9.3 Lesson 2, the integral test in P series. Our objectives for today are you'll be able to identify P series, and you'll be able to use the Convergence of P series theorem to determine whether a P series converges or diverges. So our vocabulary for today is P series. So here we have Theorem 9.11, Convergence of P series. And first of all, for our first objective, how do you know if you have a P series? A P series has this form. Sometimes it will be very obvious that you have a P series because the series will be written in a way that closely matches the form that you see here. And other times you may have to determine that you have a P series because perhaps you're just given the first few terms of the series, and you have to determine that if you were to write it using summation notation, the formula for the nth term would resemble what we have here, 1 over n to the p power. And p would be a fixed value. So that's how you identify P series. And as far as determining whether a P series converges or diverges, it is very easy. Much like it is easy to determine if a geometric series converges or not. You just looked at the absolute value of the common ratio. Here you will just look at the value of P. So if you have a P series, it will converge if P is greater than 1, and it will diverge if P is greater than 0 and less than or equal to 1. So P has to be positive. So we remember that, and the proof relies on the integral test and the proof of Theorem 8.5, which states that if you have an improper integral of this form, it will converge if P is greater than 1 and diverge if P is greater than 0 but less than or equal to 1. Because remember, the integral test says if the test is applicable, if your function is positive, continuous, and decreasing for x greater than or equal to 1 or some other integer, then you look at the convergence or divergence of the corresponding improper integral, and if the improper integral converges, the series converges. If the improper integral diverges, the series diverges. So the proof of the Theorem 9.11 relies on Theorem 8.5 because that's about the convergence or divergence of this improper integral, and it also relies upon the integral test. So we won't look at the proof, but we talked about how it would be done. And now we're going to go ahead and just take a look at a couple of examples about convergence of P series. So here is our first example, and this is it has the exact form that we have here, so it's very easy for you to identify that what you have here is a P series, because the nth term is written as 1 over n to some fixed power, and that fixed power is 5, and that's our P value. So we have P is equal to 5, and because 5 is greater than 1, by this theorem, we know that this P series converges. And that's all you've got to do. And this is enough. So you're going to cite the theorem to state that this P series converges. So all you have to do is state that you have a P series, state what the P value is, and then state your conclusion that the P series converges by Theorem 9.11. Since P is greater than 1. So here we're taking a look at number 33, and we have an infinite series because we have an infinite sum. But we don't have it represented using summation notation. So we'd like to first do that where we write a formula for the nth term in our infinite series, and then using that we'd like to determine if we have a P series or not. So to determine what the nth term should be, you want to look at a pattern that you see in the first 5 terms of this infinite sum. all of the numerators are 1. So we can begin by writing 1 for the numerator. And if you look here, this would be corresponding to n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5. So the denominators, the first one, we just have 1 for the term, but you could also write in the denominator 1 times the square root of 1, because 1 times the square root of 1 is 1, and 1 divided by 1 is still 1. But when you do that, you're able to see the same pattern hold for all of the denominators. Namely, you will have whatever n is, and then the square root of n. So the question then becomes, is this a P series? So you've got to compare it to what the form of a P series is, which is, again, as we have here, from n is equal to 1 to infinity of 1 over n to the p. It's almost in that form, but you do have to do some algebraic manipulation. So you're going to go ahead and write this as from n is equal to 1 to infinity of 1 over n times the square root of n. You can write that as n to the 1/2. And here you have a product of two powers with the same base. And the base is n. So when you have a product of powers with the same base, you add the exponents, and this gives you n to the 1 plus 1/2 is 3/2. So now you can see that we do in fact have a P series, because we have a series that matches the form of a P series. So now that we've identified that we have a P series, the next task for us is to determine the value of P. So the value of P is equal to 3 over 2. And to state the conclusion, you just refer to the theorem, which states that if the value of P is greater than 1, then the P series converges. And you can state your conclusion, as I have done here. You would just write, since we have a P series, and P is equal to 3 over 2, it converges by theorem 9.11. And that's all you need to do. So now we're going to take a look at an example of a P series that diverges. Like our previous example, what we have here is an infinite series, but we don't have the infinite series represented using summation notation. So you'd like to first represent this infinite series using summation notation so that you can verify that what you have here is a P series. So to do that, you need to observe patterns that you see in the first 5 terms of our infinite sum. So you can see that all of the numerators are 1, so we can safely write 1 for the numerator. And then for the denominators, there is a pattern that you can see. So this is n is equal to 1. This is the term for n is equal to 2. This is the third term. This is the fourth term. And what we have here is the 5th term. And although the first term does not have a denominator, you can write the denominator as 1. But you want to write that as the cube root of 1, so that the pattern that we see in the other denominators can be also used to write the denominator of the first term. So we can see that the pattern is that we have the cube root of n. Actually, we're going to write that as the cube root of n squared that we have in the denominator. Because what you can see here is that we have 4, which is 2 squared. We have 9, which is 3 squared. We have 16, which is 4 squared. And we have 25, which is 5 squared. So we're going to write here 1 as 1 squared, because 1 squared is still 1, but this will, of course, maintain our pattern for us. So we have the cube root of n squared as our denominator. Now that you have that, you are closer to having it in the form of a P series. And of course, this is what we mean by the form of a P series. So we're almost in that form, and all you have to do now is to use algebra to write it in that form. So we have from n is equal to 1 to infinity. And in the denominator, we have the cube root of n squared, which you can use properties of exponents. First of all, if you have cube root, you can write that as raising to the 1/3 power. So the cube root of n squared can be written as n squared raised to the 1/3 power. Raising to the 1/3 power is the same as taking the cube root. And then the next thing that you want to do is use a property of exponents. When you have the power of a power, you can multiply the exponents. So you will have n to the 2 times 1/3 is 2/3. So now that I've done that, I have my series represented using sigma notation, and I can see that what we have here is a P series because it matches that form. And the value of P is 2/3. So we have a P series with P is equal to 2/3. So we can see that using theorem 9.11, this series will diverge because our P value is greater than 0 but less than or equal to 1. Therefore, our series will diverge by theorem 9.11. And your conclusion would be stated just as I wrote here. Since we have a P series with P is equal to 2/3, it diverges by theorem 9.11, and that's all you've got to do. And also remember, if P is equal to 1, your P series will also diverge. And that is called the harmonic series. So if you have, for example, this P series, where P is equal to 1, it would just be written like that. It's called the harmonic series, and it also diverges by theorem 9.11. So today we looked at P series, and the first thing that you've got to do is to identify that you have a P series. And once you've done that, it is very easy for you to determine whether your P series converges or diverges by using theorem 9.11. Of course, if you know that a P series converges, you will not know what value it converges to. You just know that it converges. So this adds to the list of tests that we've been learning to determine the convergence or divergence of series. We began with telescoping series, which uses the definition of convergent or divergent series, and then we looked at geometric series. And then we looked at the nth term test for divergence, and then we looked at the integral test, and now we're looking at P series.